So let me introduce Ceyda now. Welcome back, Ceyda. Thank you again. She received her undergraduate and master's degrees from Boğaziçi University, which actually support this conference by getting an access to Zoom info, as you can see from the link. And after graduating from Boğaziçi University, she joined the Groningen University, and she is now working in the research group of renowned physicist Eric Bergshoeff. Her recent research topic is the low energy dynamics of non-relativistic string theories. And today her talk will be an introduction to this non-relativistic gravity. So thank you again, Ceyda, for your time. I will warn you when you have only 5 minutes, but you can have like 5 more extra. Now screen is yours.
Yeah, thanks a lot. Thanks for your introducing me. Well, as you already realized, I changed the title. Well, it's more or less the same title, but anyhow. So this presentation based on work in progress with my supervisor, Eric Bergshoeff, and collaborators, Johannes Lahnsteiner, Jan Rosseel, and Luca Romano. So if you have any comments or questions, I would appreciate if you ask immediately. We can also discuss in Q&A session, but you are also welcome to interrupt me. So let's get started. The plan is following. I will try to give kind of long motivation why non-relativistic symmetries are important, relevant, by providing some specific examples. And then I will try to introduce some basic concepts in Newton-Cartan theory, which is the diffeomorphism covariant description of Newtonian gravity. And then I will generalize this idea for extended objects, in particular for strings. And as a last thing, I will talk about my research, and that will just come at the end. Okay. So this is the timeline which is important for this talk. It starts with Newton, Principio from Newton, but the true timeline I would like to present here starts with the plague of London, ravaged the British city in 1665, and Newton was a student in that time at Trinity College in Cambridge, and he basically escaped from Cambridge to his parent house, and he was kind of isolated for, I think, more or less 2 years, and he changed the world in quarantine from plague. So here we are. I'm not sure how optimistic starting point here, but there is some kind of interesting history and relation with our time. And his mechanics, his theory based on absolute time. So for his theory, space and time is decoupled notions, and he introduced Newtonian gravity as a force between two massive objects. We all know. And then many years later, Einstein improved the gravity theory, and what we know, now we call general relativity, which is kind of new understanding of gravity compared to Newtonian one. And it based on the idea that gravity is not a force, actually, it is geometry. And basically he geometrized gravity in the language of differential geometry. After 8 years, Cartan come up, show us how to geometrize also Newtonian gravity. Okay, that sounds reasonable, I believe. And so this is my motivation. So I think in itself, geometrization of Newtonian gravity has its own interest. Once you understand general relativity, it's natural to ask, okay, is it something related to relativity, or it's more like notion of gravity is related to this geometric description? And the answer is, it's nothing with relativity, it's the gravity that inherently observes geometry. The first field which we see non-relativistic symmetries is post-Newtonian approximation. I think it's great that we saw gravitational radiation in our decade. It's fascinating. It's amazing work done by experimental physicists. And gravitational radiation is a crucial prediction of general relativity, as we all know. However, general relativity is a highly complicated nonlinear tensorial theory. Almost no physically useful exact results are known. And for that reason, our main understanding of gravitational radiation based on some approximation. And one class of approximation is post-Newtonian approximation, which is limited to weak gravitational field and slow motions. And recent studies after that detection show that post-Newtonian approximation is unreasonably effective to describe phenomena like neutron stars, binary neutron stars inspiring toward the final merge. Okay, one thing I should say, okay, we see non-relativistic symmetry is there, but post-Newtonian approximation is in general not a coherent description, but okay. The second application or second theory we see is modified Newtonian dynamics, suggested by Milgram in '83. So this theory is motivated empirically in order to replace dark matter. And because it is inherently non-relativistic, it fails to provide relativistic phenomena like gravitational lensing and so on. For this reason, relatively new work done by Bekenstein, and he embedded this theory in a relativistic setup in order to solve these problems. And even well, of course, there are many more works which I'm not aware of much, but this is like basic line. I kind of have an idea. At the beginning of this year, Lavinia Heisenberg and her collaborators embedded Mond in coincident general relativity, where you discard non-metricity condition, and they provide some predictions and some application on the galactic and cosmological scale. So it's quite still alive theory, I would say. Another concept, well, another system is condensed matter physics. So in condensed matter physics, non-relativistic conformal theories arise, and the aim there, well, one of the aim is being able to manage with strongly correlated systems. As Umut Gürsoy mentioned yesterday, one way of dealing with strongly correlated system is using the technology called holography. Once you have non-relativistic symmetries, then you would expect some non-relativistic holography. So, for example, non-relativistic conformal field theories, which are relevant for the condensed matter physics, they have potentially have some gravity dual. Another approach, at least my motivation or our main motivation is quantum gravity, trying to get some intuition about quantum gravity, approaching from some non-relativistic theories. When I say quantum gravity, in my mind, there is string theory. So I will just go in that direction. So to be able to a bit motivate that point, so this is the Bronstein cube. It represents a space of physical theories parameterized by natural constant, speed of light, Planck constant, and Newtonian constant. So the final thing, we want to approach quantum gravity, right? But there is one way you can go from general relativity, or you can go from quantum field theory. Well, one technical question, it's not guaranteed that these two arrows will converge to the same point, but okay, it's general issue, I will say. And another approach, well, I think this Bronstein cube at least suggests that there's a third way you can approach the quantum gravity, and that is actually non-relativistic quantum gravity. Okay, So in that sense, it is kind of natural to consider some non-relativistic quantum gradient approach to final result. Okay, so I will start quite basics. So I already mentioned that Newtonian gravity based on absolute time, it is frame-dependent formulation and contains instantaneous interaction. One simple, well, obvious observation I would like to make with you is following. So consider particle in a flat 3D space coupled to Newtonian potential in that form. I think we all know that equation of motion. On the other hand, in the relativistic, well, in GR, one of the first things you see is geodesic equation, where particle couples to general background. And this geometry is packaged in this connection, gamma. And if you just stare these two equations a bit, you can immediately say, okay, can I associate connection with Newtonian potential? Once you do that, you already start to kind of geometrize gravity, I will say, Newtonian gravity. And even further, you can ask, okay, what is the remaining tensor corresponding to that connection? So, okay, you can do that. And then you see, okay, there's a double derivative, special derivative acting on phi. Even you can calculate the equation of motion and you would get Poisson equation. It's not surprising, of course, but it's not really systematic way. It's just one basic observation I wanted to present here. But the question is, how can we systematically geometrize Newtonian gravity and try to get more covariant formalism? The way I focus in this talk is limit, but there's other ways. I will just name them. So one approach is expansion. I think we have expert in the audience. I saw Mert Ergen in the audience. Another approach is null reduction. It's kind of Kozak-Klein reduction where Killing vector is null. The other one, I think some double field theorists taught me that they can also geometrize Newtonian gravity in that setting. And possibly there are many more, but they are at least the ones I remember right now. Okay, so let's get started. I mean, I should describe the limiting procedure. And for this, let me say a few things about the causal structure. So on the left-hand side, you see relativistic particle and the light cone, and the light cone towards the time direction. So this is the diagram on the left we all know very well. And I want to take the non-relativistic limit, and when I took the non-relativistic limit, then interactions should be have infinite velocity, right? If they are instantaneous. But how I really think limit. So when I take the limit, I'm thinking that there's some velocity of a particle, which is much smaller than speed of light. But what is that velocity? Basically, I'm imagining that the velocity of particle in space, not space-time. And basically, I'm considering that the motion in space is much smaller than motion in the time direction, because time direction, in a sense, goes always with speed of light. And for example, you can extend this idea for extended objects. I will come to that in a second. But first, let's have a look on this light cone. What happens when I take the limit? Basically, that opens up the light cone, because having instantaneous interactions means that in the light cone you have horizontal line. And if you want to extend this idea for extended objects, then you have a word sheet instead of word line. And for example, your string propagates in transverse directions, which is d-2, since word sheet is two-dimensional. And you can even extend this idea for like p-branes or whatever to your favorite object, and it can be done. So the important message here is that I have to treat longitudinal and transverse directions differently in order to take limit. That's the main message of this slide. Okay, so let's have a look how I can take the limit. So consider a relativistic particle. This relativistic particle, I'm not sure whether you are familiar with, but I just introduced some Lagrange multiplier for Lagrange multiplier E. If you just would solve for E, you would get the usual action with square root. I don't really want to work with square root. The reason is in string point of view, it's natural to work with Polyakov action instead of Namu-Goto action. And here I will use Vierbein formalism. So I write down the metric in terms of relativistic Vierbeins. Okay, and the important point is I can't take the limit directly from this action. I have to couple to charge particle. Sorry, I have to couple to charge. So for that reason, I introduce gauge field B mu. And then, as I promised, I decompose tangent space to longitudinal and transverse. And the recipe, in order to take limits, sorry, this shouldn't be there. The recipe I want to introduce in order to take a limit is following. I make some redefinitions for relativistic fields by introducing contraction parameter omega. So E mu 0 is expanded in that form, well, redefined in that form. E mu A prime is like this, and B mu goes by first some kind of divergent term, divergent in the sense that at the end I will take omega to infinity. And when you just plug in this expansion into the action, unfortunately, the work didn't done yet. The reason is there's a divergent or omega square Lagrangian, which is the leading part of the Lagrangian when you insert this expansion. However, this divergent term is compactified in omega square, in a square expression. And if you have a square expression as a divergent term, there's a trick, a known trick. You introduce some Lagrange multipliers, lambda here, and rewrite the same term here by introducing Lagrange multiplier. And the funny thing is that if you solve for Lagrange multiplier lambda here, you go back to that action, this one. But if you take the limit on the right-hand side, this is a finite Lagrangian, which is what we want to get, because there is no divergent omega, well, there is no positive power of omega, which is good. And then, okay, I'm just skipping some steps, but I hope you can believe me. At the end, you get this action. So I claim that this is the non-relativistic action coupled to metric H mu nu and gauge field B mu. And H mu nu is given here. And well, it's not surprising. When you expand G mu nu, you would get some omega tau mu 0, beta 0, 0 plus H mu nu. So that is just came from definition I didn't made up. And the basic Newton-Cartan fields are tau mu, E mu A prime, and M mu. They are subjected to local spatial rotation and Galilei boost. Okay, good. But how, well, I should be able to extract some notion why this is the non-relativistic particle. For that, you have to go to the Galilei frame by fixing by doing some gauge fixing, namely the gauge fixing I introduced here. So the Newtonian potential would occur in M00. And if you just plug into this action would give you the equation of motion I introduced at the beginning. Okay. that's good. I can reduce the covariant action to non-covariant action and get the right result. But one important observation is that non-relativistic particle couples to these Newton-Cartan geometry fields, but cannot couple to B-mu field independently. The reason is that if you just plug H mu into this action, you would get something like that. Oops. So this is the special part minus x dot mu m mu plus b mu. So from particle point of view, the coupling only sees a combination of m and b. That means that for particle, it cannot distinguish whether it couples to m or b. Another way of saying is there is a Stueckelberg symmetry. If I shift b by this amount, c mu, and m by c mu, then this combination is invariant. This suggests that in the way of introducing fields, there is some redundancy. I introduce some redundancy, but in principle, I can just fix them by saying either m mu to 0 or b mu to 0. That would be equivalent description because particle cannot distinguish them. And I should say that if you want to set m mu to 0, then you have to be careful because m mu field transform under local special rotations, but it can be done. So one thing is, what is a mu field if you are not familiar with this setting? So let me give my answer. From the algebraic perspective, a mu field is a gauge field of central extension in the Barkman algebra, which I didn't mention that yet. To understand the Barkman algebra, let's have a look on non-relativistic particle. I think we use that Lagrangian many times, starting from maybe even not high school, first year undergraduate maybe. And under Galilei boost, if you just transform by this, you will see that action is invariant, but Lagrangian not. Lagrangian is invariant up to total derivative. And if you just calculate the Poisson algebra, you will see that actually commutation relation of boost and momentum is not 0. It's proportional to mass. I think I messed up with indices, but there should be something like, let me see, A, B, delta A, B. Because there is more than one dimensional boost, basically. Okay, and this is called Galilei algebra, if that is, this commutation relation is proportional to M. Okay, but still I didn't make the connection with M mu field. This connection can be realized easily from gauging algebra perspective. So let me briefly say what would happen for the GR. So if you start with Poincare algebra and gauge it, I'm not sure whether we are on the same page, but by gauging, I'm saying that, so for algebra, for every generator, you have transformation parameter. So let's say psi A hat and lambda A hat B hat. So this is translation, this is Lorentz transformation. And if you want to gauge it, that means that you want to make these parameters local, space-time dependent. And the cost to pay is that you have to introduce gauge fields corresponding to these transformations. This is something we always do. Well, one simple example is if you have Lagrangian with complex scalar field, you have U1 symmetry. I think I mean, in quantum field theory, I think many people, I guess, saw it. And if the transformation under U1 is just E alpha phi, and if you want to make that local, the parameter local, you have to introduce a mu field. And this is exactly the same thing happening here. Oops, sorry. That was just a side remark. And then from the algebraic perspective, these gauge fields are completely independent objects. However, in general relativity, I know that spin connection can be described in terms of phi-bond. And to do that, I have to introduce so-called conventional constraint, which relates spin connection with phi-bond. And that is the conventional constraint I wrote down. That is basically curvature of phi-bond is equal to 0. And then you would get the kinematics of general relativity. Similarly, once you get the Barkman algebra, you can gauge it. And the gauge field of M in the algebra would be mu field. That is the point, that is the relevance between the gauge field and central extension. And then you would get Newton-Cartan geometry. That is, I think, expected. The problem here, well, not problem, but different concept, well, different than relativistic case, at least. Not all constraints are conventional in the sense that not all constraints can be used to solve for spin connection. And especially this constraint I wrote down here cannot be used for spin connection because there is no spin connection there. And that is just the constraint on the geometry. You should take it. And that is known as zero torsion. I think I will come to that point later. But the zero torsion actually brings us absolute time. So because of this constraint, let's imagine some hypersurfaces, special hypersurfaces, and you want to calculate the time difference from point A to B. So for that, you write down the integral dx mu d mu, tau mu. And the solution for tau mu from this constraint is just, if I just solve tau mu in terms of a function, that would be d mu tau. And the time difference between these 2 points are just given by endpoint values, because this is just total derivative. In other words, if you just apply Stokes theorem, that would just give me, not Stokes theorem, sorry, it's just boundary terms. So this is just the value on B minus value on A. So it's independent of path taken by different observers. So that is the notion. Absolute time came in the Newton-Cartan theory. This constraint can be discarded in different situations, but maybe I will come to that point later. Okay, is there any questions so far?
I have a question. What does the B mu field corresponds in the earlier pages?
So B mu field is kind of Maxwell field, in a sense. Well, at least you would think like that. But the way well, one thing, I can't see B mu field in the algebra if you are asking that. Because I mean, for example, in Poincaré, when you introduce gauge field A mu, that A mu, the algebra of A mu would be U1, but that would just...
Yeah, Maxwell equations.
Yes, but I mean, it's not in the Poincaré, it's just a cross product of U1. Cross, well, Poincaré cross U1 would give me a Maxwell theory. So one way of thinking is, I'm not sure whether that would... Yeah, maybe I didn't understand your question. Can you say again?
No, it's all right. I get it now. Thank you.
One maybe side remark would be, if you would start with Poincaré cross U1 and apply Inoni-Wigner contraction, which I can't give the recipe for that, then you would get immediately Barkman algebra. So that would be an algebraic way of getting Barkman starting from relativistic algebra. That is somehow, well, not somehow, it's directly related to what I'm doing here, because in some sense I introduced the same here.
It's a gauge field, yeah.
Yeah, it's a gauge field.
Thank you.
Problem.
So may I ask one more question?
Sure.
It's again about Barkman algebra. So
Yeah.
you told us that Barkman algebra is the central extension of the Galilean algebra.
Yeah.
Well, So normally for general relativity, we know the action. Einstein gave it to us, but we can write it. So do you have any action for Newton-Cartan gravity?
Amazing question. Can I come to that question later?
Yeah, why not?
Well,
we can do that. But
the
also,
answer
let
is
me ask another
yes and
question
no.
then.
Okay.
Huh?
The answer is yes and no.
Okay, then let me ask another question. So you have this conventional constraints, right?
Yeah.
Who told you to put it there? You did it by hand, right? You
Well,
implied
one
that
thing
you
is,
imposed it by hand.
yes, but one reason is, so you know that P translations can be written as general coordinate transformations, and to do that you have to put a constraint, right? Otherwise you can't associate gauge field with phi by.
So okay, if I want to like express my favorite non-relativistic field theory,
Yeah.
should I always start with some relativistic field theory and then find the appropriate constraints, maybe according to which gauge fields I have, up until I have a unique connection, so to say? Is this the way to go?
Well, this is one way to go. For sure. I mean, the reason is, for at least for me, taking limit is more fundamental than trying to get something from nothing, because at least, I mean, there should be correspondence with relativistic theory and non-relativistic theory. There is different approach, as I said. One, yeah, of course. I mean, if I just give you the underlying symmetry, you can write down action without considering any relativistic theory. I can imagine that scenario, but I think it's kind of a matter of taste. I can't say that this is a unique way to get non-relativistic theory.
Okay, thank you, Ceyda.
For me, it's more relevant than writing something which is non-relativistic, but without knowing the relation with the relativistic theory, it's less appealing for me.
I guess it's also in the spirit of also Brownstein's cube, right?
Yeah.
Thanks. Okay.
Okay, so for this part, I will focus on string. So I will start with the relativistic worldsheet action. And so the string theory based on, well, it's a theoretical framework where particles replaced by extended objects, so-called strings. And because they are extended, instead of word line, we have worldsheet. So you see from this action. So let me introduce this action. H is a independent worldsheet metric. G mu is a space-time background field. B mu is a Kalpromont field known in the string literature, and there's possibly some dilaton term. Basically, B mu field is analog of gauge field in the particle case. And similarly, I decompose the tangent space as A and A prime. This time, A can take the value 0 and 1, and A prime is D minus 2. And then I do exactly the same expansion. I just replace 0 by A. That's all I'm doing. And I introduce how B mu should expand it or redefine, let me say. And I'm doing the same procedure. I end up with some omega square leading Lagrangian, and to be able to deal with this divergent term, I introduce Lagrange multipliers. You see in this finite action. And what I'm saying is that this is the analog of particle action in the string case. So again, H is the independent worldsheet action. H mu is our metric. B mu is Kalpromont field, and there is some time-like. Well, let me write down this maybe. So tau mu is tau mu 0 plus tau mu 1 with some normalization, but I mean, it's not that important. It depends on tau and with some coordinate change. And this action can be obtained by taking limits. Omega goes to infinity limit. And similarly, this non-relativistic action also cannot couple both a mu field and B mu nu field completely independent way, again, I end up with some Stueckelberg symmetry, and this Stueckelberg symmetry can be realized by these transformations. So again, if I just plug this transformation into the action is invariant, which means that there is some redundancy in the way of introducing fields, background fields. So from now on, I will set mu A to 0 for convenience and work with B mu nu, and from now on, I won't have any Stueckelberg symmetry. Okay.
Sorry, Ceyda,
Yeah.
you have 5 minutes. But
yeah,
we can extend it like 5 more if you need it.
Okay, good. So first, let me say a few things about string theory. In the string theory nonlinear sigma model, fundamental object you would start with, and actually it contains much more information than you can imagine. And the important or magic behind it is that because sigma model has two-dimensional quantum field theory, if you just say that, regard that this Bergshoeff action has while symmetry at the quantum level, you determine the dynamics of space-time. That is, I think, amazing thing about string theory. You just start with the non-relativistic nonlinear sigma model, and you get some information about space-time. So what I mean, so that would be naively some analog of Einstein equation, but this time you would have more fields. So that would be vacuum Einstein equation, but coupled to different, also different fields. So one easy question is there any low energy effective action? Jem already pointed in that direction. And then supergravity came to the game. Oops, I can't write anymore. Okay, but okay, let's see also in the non-relativistic setting, we get non-relativistic sigma model, nice. Then the same procedure works. You can do one loop calculation and get the low energy dynamics of non-relativistic geometry. That is already in the literature done by Zikian, Jaume Gomez, and their collaborators. And the naive question is that, is there any non-relativistic low energy effective action? And this, I don't know the answer yet. Well, I will give a partial answer about that. And also, if there is a non-relativistic low energy effective action, the question is whether this action can be obtained from the relativistic one. That's also a different question because it's not guaranteed that they will emerge to the same point. Okay, let me try to speed up. So I just start with dynamics, well, supergravity action, only I see gravity, Kapp-Bromont field in H, so as defined here, and some dilaton kinetic term. And this action is in second order formalism. I don't even know whether there is first order formalism for this action. So second order formalism, which means that spin connections are solved for phi bind. And if you just do the same expansion, the Ricci scalar goes by omega square. I got the same trouble. So the leading term is R square, R2, and R2 is proportional to tau square, so some curvature of tau. This shouldn't be surprising because in the expansion, the only positive power expansion in the tau. So if you just go back to, if you just go back to the expansion, the only field goes by omega is tau. So it's not surprising that we get some tau square term in the divergent part. But the surprising thing is that since we also expand Kapp-Bromont field, the divergent term coming from Kapp-Bromont and Ricci scalar, they just cancel each other. That is surprising because there's, I mean, in some sense, that happened in the nonlinear sigma model, but good enough that also happens in the low energy effective action. That is, well, consistent, nice story. And then, okay, then you get the finite term and with some expansion in dilatation and Kalb-Ramond field. So that is the non-relativistic action. Let me introduce. So R is just a curvature of special spin connection. Taus are just there for some covariantization. So this is the modified dilaton kinetic term, and I have some H where H mu nu rho is defined by with non-relativistic Kalb-Ramond field. And the reason why I wrote down this kinetic term in that form is because of emergent dilatation symmetry, which is not there in the relativistic case. So if you transform tau mu by lambda and d phi is just a shift, then this action is invariant under dilatation symmetry. And since d phi is not covariant object under dilatation, it requires some kind of spin connection, and BA prime defined here. And in some sense, BA prime plays the role of spin connection for the emergent dilatation symmetry. Okay, the deed book. So due to the emergent dilatation symmetry, one independent equation of motion less than in relativistic gravity. So if you have more symmetries, then you have less equations of motion, less degrees of freedom. And the missing one is actually analog of Poisson equation. And now I'm answering James' question. That is well-known problem also in Newton-Cartan theory. It's highly non-trivial to get Poisson equation out of non-relativistic action. There's different ways to get Poisson equation, but the cost you have to pay is that you have to introduce many more fields than what you introduce here. So instead of getting, well, instead of introducing Newton-Cartan basic fields, you have to introduce more fields to be able to get Poisson equation. So it's a bit complicated, but it's also a well-known problem in some sense. But then you can ask me, okay, if Ceyda, even you don't get Poisson equation, what you are doing here? So let me motivate that. So previously we worked this low energy dynamics at the level of equation of motion, and there we were a bit more restrictive. We impose immediately zero torsion constraint in order to get a non-relativistic limit. And from this action principle, we realized that actually we don't really need to impose a geometric constraint as a starting point. I can get non-relativistic low energy action without imposing any equation, any constraint on the geometry, which is super nice for the following reason. So our main motivation was going to non-relativistic supergravity or non-relativistic superstrings. And if your theory is only defined up to some constraints, you might be in trouble. The reason is following. That is partially done. Well, that is done in particle case when you have Newton-Cartan and supersymmetrize. If you have a geometric constraint, as here, this geometric constraint should lead many more constraints when you supersymmetrize. So, for example, this constraint, if you supersymmetrize, that will give me some constraint on curvature of graviton. And if you just even supersymmetrize, that will give another constraint. And it's not guaranteed that that will stop. You may end up with like over-constraint system. But if you get this torsion constraint as a result of equation of motion, it's guaranteed that it will stop, because equations of motion will they are just a closed set, and when you just transform transform under supersymmetry, it will just go to another equation of motion that is guaranteed. So in some sense, even we couldn't get the Poisson equation, we have this Poisson equation, which with the calculation obtained on shell at the level of equation of motion. So in principle, this equation of motion, this action almost give every equations you need except Poisson, and I can just supersymmetrize this Poisson equation by hand, if that is the only problem you have. Okay, so let me see. Okay, I think more or less I said everything here, and I'm not sure how I'm doing with time. So maybe it is better to clarify a bit this Poisson thing. I think since 1994, it is well-known fact that it's not easy to get Poisson equation from the action. One attempt was the null reduction of GR, Newton-Cartan, let's say, and they realized that they can't get Poisson equation. And this theory, in principle, we didn't know the relation with limit. Well, let me write down in this way. So at the beginning, I mentioned that there is different approach. One is null reduction. The other is limit. And in principle, we don't know the relation between them. But we derived the non-relativistic T-duality rules. And we actually realized that T-duality along the longitudinal direction in string theory goes to the relativistic theory with null isometry. So there is some relation with null reduction with string theory via T-duality, and that makes the connection with null reduction and limit here. Because if you do the null reduction, you also can't get Poisson equation. But I'm saying, okay, let me say in this way. If you would, if you do T-duality, you get relativistic theory with null isometry. Whereas in the other edge, you would get non-relativistic string theory. And similarly, I'm expecting the similar thing at the level of low energy effective action. And that is also known that the action with null isometry cannot give you Poisson equation. The basic reason is that you set null, G UU to 0, then you can't get the equation of motion for that metric component. Well, I'm not sure whether maybe that became a bit more complicated, but if you have any questions, please ask. I will end here. I will stop here.
Thank you very much. Do we have any questions?
Can I ask one question?
Yes, please.
We know that Newton's theory of gravity, the gravitational forces are always attractive. Can you avoid getting repulsive gravitational forces in your formalism?
Repulsive.
Repulsive gravitational forces. Vector fields give rise to repulsive forces.
Well, in some sense, I think I don't have repulsive forces here.
How can you guarantee that?
Well, because well, I can't guarantee it, I guess, but the reason why I believe that, for me, mass and charge is same thing. Electric charge. Why it's same thing? Because
electric charge can be negative.
Yeah, I know. It's something I didn't understand completely. The reason is, when I introduce here, you would see that electric charge, right? But I put M. So in some sense, it's kind of BPS condition. I already relate mass with charge. And otherwise, I can't get non-relativistic limit. I'm not sure whether I can
electromagnetic degree of freedom. Are you sure that this is an electromagnetic degree of freedom? You should look at how it couples to the electric charges.
I think I can also add electric charge by hand. You are right.
Okay, I mean, if you can.
Yeah, but I mean, in that setting, I would say there is no repulsive interaction. I don't see how you.
Well, in supergravity there are. The point is, they are short range because.
Yeah, I think I should think about it. I'm not so sure.
Okay.
Yeah,
okay. It's just I wondered. But there, you should look at it. I think there is the possibility that there will be some repulsive gravitational forces, and I think you wish to avoid them.
Yeah, but I mean, the way, in some sense, I avoid them, at least in that setting, I mean, I don't know. So, for example, in some sense, I'm doing the same thing here. And for me, I didn't introduce true gauge field. I introduced mass coupling in some sense here. There is no electric charge. Yeah, I think I agree that I avoided, but maybe I'm not aware of how I avoided that.
Well, okay.
Thanks.
Okay. That's fine.
Any other questions?
I would like to ask a question, but if the answer is too long, I can ask you later, Ceyda, because I would like to ask you more questions eventually at some point.
That's good.
Okay, so for instance, Cartan's perspective of general relativity, torsion has a central role. He was one of the advocates of that. Do we have in the non-relativistic context torsion full non-relativistic geometries should be physically very important, because for instance you can think of a hydrodynamical system with internal torque or internal spin, spinning sort of a fluid, then torsion would come into play in such a field theory. Can you comment on that? Because you had zero torsion constraint as well, right?
Yes, but I think if you have matter coupling, you can allow for torsion. And I mean, maybe I didn't stress enough, but in the last, well, the way we take the limit, here there is no zero torsion. There is just Twistis torsional theory. So
maybe I missed that part. My bad.
Yeah, no, I didn't say explicitly. So I don't need to, because I didn't give the equations of motion. As a defining limit, I don't need to impose zero torsion. Partially, I get torsion type of constraint. So let me write down explicitly. So I can't avoid this constraint. Or let me say, it's better to write in light concordance. This is just minus. It's not that important, but it is why I'm giving in that form, because it is invariant under supergravity. That's why I wrote in that form. And there is some dynamical equation you can solve, and this dynamical equation is compatible with zero torsion, but it would be just solution of equation of motion. So a priori, you don't have to impose full zero torsion
constraint. Okay, thank you. And I will ask you more questions later. Thank you for the talk as well.
Are there any other questions? Maybe one last question.
I don't want to occupy the last slot, but I have a layman's question or laywoman's question. So I'm a little bit curious about your motivation for the non-realistic gravity. And you said there is a link from this to the relativistic version. But how did that link work? Because from my understanding, the problem for quantum gravity, or the main problem, is that under like high energy cutoff, the metric tensor wouldn't be covariant.
Okay.
So it wouldn't be relativistic. Wouldn't be.
One thing, maybe I abused the language a bit. So this is not really relativistic because this theory has a null isometry. So if you have a null isometry, in some sense, you are already in non-relativistic scheme. It's not true relativistic theory.
Right, but how does that link work? I mean, so is it part of the motivation, or is it just quite tangent?
Well, it is just the result of T-duality. If you just start with non-relativistic string theory, take an T-duality along longitudinal direction, and then you end up with relativistic theory with null isometry. I can also give references, but I'm not sure. I mean, in some sense, both sides of T-duality is kind of non-relativistic, because I mean, if you impose null isometry in the relativistic theory, you are inherently in a non-relativistic regime, I would say.
I'm not sure I understand, but okay.
Let me interrupt. Maybe I can give your email address to each other and you can discuss if you want.
Yeah.
By the way, Liu Chen is a philosophy professor from our university. Maybe she can give some insights on the philosophy to you too. I'm taking an ontology class from her.
Yeah, I would love it.
Welcome, man.
Yeah, this is my email address. Yeah, thanks.
Thank you.
Okay. Thank you for the questions, and thank you, Ceyda, again. Have a nice day. And we will have like 2 or 3 minutes break, and we will continue with the next speaker.